So come on. Okay. So let me mute that. Okay, I think we're good to go. All right. So you said number 8, right?
Yes.
Okay, you want to go through all of number 8, or is there a particular?
Well, I get part A. I just had like
Okay,
a question. So like when we're trying to solve for the molar solubility, so KS.
hold on. Whoa, you said number 8
Yes.
for assignment 5? Oh, okay, I know what happened. My bad. Hold on. I'm looking at an old copy of the assignment and the numbers are different. Okay, assignment, okay, number 5, which says, what is the concentration of saturated lead chloride solution?
Um,
Oh, no, that's number 5, I'm sorry. Calculate the molar solubility.
yes.
Okay, that one, okay. So
So
basically, okay, go ahead.
okay, so it's a pretty basic problem. Like I'm seeing what we went over in class, but
Hmm.
so for so for these types of problems, when you set up your
Hmm.
ice table,
Hmm.
you don't need anything for the products, right? Because KSP is only for the sorry, you don't need anything for the reactant, right?
Exactly, because the reactant is basically based on how the equation is set up. The reactant would be a solid. And if you remember, we said, and this was from the first equilibrium chapter that we did, I think it was the 3rd chapter. Remember, we said that if you have a solid, a pure solid or pure liquid involved in the equilibrium system, then those will not be in the equilibrium expression. And the reason why is because the concentrations of solids and liquids are constant. All right? So because they're constant, that means that we simply ignore them. So for example, in the case of the lead, let me share my screen here. In the case of the lead chromate example in this question, so let me draw. So in the case of PbCrO4, why is it looking like this? O4, this is a solid, right? And it
Mm-hmm.
will be in equilibrium with Pb2 plus aqueous plus CrO4 2 minus aqueous, right? So because this is a solid, when we're writing down the equilibrium expression, KSP, that would only contain concentration of Pb2 plus times the concentration of CrO4 2 minus, and that's it.
Okay.
Mm-hmm.
Okay, so I think I pretty much understand that one because yeah, that was pretty simple. But
Mm-hmm.
for part B of this, could
Okay,
we go
good.
over
Uh-huh.
can we go
All
over
right,
that?
so yeah, we can do that. Let me delete this here. Okay, so in the case of part B, the ice table that you're going to use is, well, let me write the equation first down. It's going to be PbCrO4, and then that will dissociate to form Pb2 plus aqueous plus CrO4 2 minus aqueous. Now, the thing is, the question is asking for the molar solubility of lead 2 chromate in the presence of 0.20 m sodium chromate. Now, the sodium chromate, I'm just going to squeeze it up top here, is going to dissociate first, right? To form 2Na plus aqueous plus CrO4 2 minus aqueous, right? So because this dissociation is complete, the first one, whatever the molarity of the sodium chromate is, ultimately the molarity of the sodium chromate is going to be the same. So when you're going to set up your ice table, initially, you're going to have no lead 2 plus, but here, you're going to have 0.20 m of the chromate ion. The change here is going to be plus S, and then at equilibrium, you're going to have S here, and here you're going to have 0.20 plus I'm sorry, you're going to have, yes, 0.20 plus S, right?
So,
I'm sorry, go ahead.
the CrO4 2 minus, it's
Mhm.
0.2 because the concentrations are equal for the Na2 and the
Well,
Na2Cr.
the reason why that's the case is because the molarity of this of the sodium chromate here was given as 0.20 m, right? And
Right.
because that undergoes complete dissociation, and there's a 1-to-1 mole ratio between the sodium chromate and the chromate, that means that the molarity of the chromate ultimately is going to be also 0.20 m, right? And
Yes.
that would be the initial concentration that you're going to put here. All right.
Yes.
And then continuing, we can set up the KSP expression, which in this case is going to be equal to the concentration of Pb2 plus times the concentration of the CrO4 2 minus, right? So we put the terms in for the lead 2 plus, that will be S, so that goes here. And then we multiply by the chromate, which is 0.20 plus S, so that goes here. And here we assume that S is so much smaller compared to 0.20, such that S plus 0.20 is approximately equal to 0.20, right? So therefore, this part here breaks down or simplifies to KSP is equal to S times 0.20, which means that S will be equal to the KSP divided by 0.20. And I think they gave the KSP earlier in the question. Let me see here. Yes, they did. 1.8 times 10 to the minus 14 would be the KSP of the lead 2 chromate divided by 0.20. And when we work that out, 1.8 times 10 to the minus 14 divided by 0.20. So according to my calculations, this works out to be equal to 9.0 times 10 to the, oh, wait a minute. I think I made a mistake. Okay, the mistake I made was that up here, this should be 0.020, which means that this should be 0.20, 0.20, 0.20, 0.20. So let me redo, and this also should be 0.20. So let me redo all this here. 1.8 times 10 to the minus 14 divided by 0.020. So according to, hold on, 1.8 times 10 to the minus 14, 1.8 times 10 to the minus 14. I keep pressing the wrong keys. Divided by 0.020. So I got 9.0 times 10 to the minus 13 m. And that's how you do that.
Okay.
All right?
Yes, thank you. And I was also wondering if we can go over number 9.
Number 9.
Mhm.
Number 9. Oh, so that's the one with the indicator.
Yes.
Okay, so to start off with, the question says, in fact, let me erase all this here. Okay, so the question says, the indicator, HIND, is yellow in 0.1 m sodium hydroxide and blue in 0.1 m hydrochloric acid. And it says the pH range in which a color change occurs in this indicator is 3.6 to 5.2. Okay, so first question is, what is the equilibrium equation? So there are a couple of ways you can write this equation down. You can write it as HIND to form H plus IND minus, or you can write it as HIND plus H2O. Plus H2O to give H3O plus IND minus. Any one of these two would be sufficient to answer that question. All right? Even though the first one is actually the more realistic way of expressing it, but I will accept this just as well. All right? Now the B, so this is the A part. Now the B part is asking what is the color of the HIND. Now the hint to answering that question is in the information that was given in the very first sentence, right? The question says that the indicator is yellow in sodium hydroxide and blue in 0.1 m hydrochloric acid, right? So if you look at this, let's use this equation here to answer that question. If you add sodium hydroxide to the system represented here, the sodium hydroxide is going to reduce the concentration of H+, because what's going to happen is that the hydroxide is going to react with H+ to form water, right? So basically, the hydroxide will be removing the H+ from the system, and therefore, as a result, the equilibrium position will shift in this direction to counteract the change that you're imposing. If you're reducing the concentration of H+, the system will try to increase the concentration of H+, right? So therefore, what that means is that it's going to favor the formation of the conjugate base. Now, since the solution is yellow in the presence of base, that means that the conjugate base itself will be yellow, right? So basically, the color of the IND minus is going to be yellow, which means that as far as the undissociated molecule is concerned, that is going to be blue, because when you, the question also said that the solution is blue in 0.1 m HCl, which means that if you put that in hydrochloric acid, the equilibrium is going to shift in that direction to reduce the concentration of the H+, which means that the predominant species is going to be the undissociated molecule. So therefore, it's going to be blue in acid, and therefore the molecule is going to be blue, right? So to answer B, the color of the undissociated molecule is blue, and the color of the conjugate base is yellow.
So,
Mm-hmm.
let me see how to ask this. So like, if the indicator, if the acid is a certain color, the will the HIND always be the color of the acid?
Yes, of the acid form, right? So you have to
Yeah.
remember, you're going to have the two forms. You have the acid form and you have the conjugate base form, right? So that the indicators, the way they work is that, well, how should I put this? The basis of how indicators work is that the acid and the acid and the conjugate base would have different colors, right? So
Oh,
basically, in an acid environment, the acid form would be the predominant species, and therefore the color of the solution would be the color of that species. And then if you put it in a basic environment, the opposite is true. The conjugate base will be the predominant form, and therefore the solution will take on the color of the conjugate base. So it's all a matter of which one would predominate. And you can adjust that by either adding acid or adding base to your indicator.
okay.
Mhm. All right.
Yeah.
So that's the B part.
And
So
I
go
pretty
ahead,
much
sorry.
understand part C, so we can skip
Okay.
that if you want.
Mhm.
But part
So,
D,
mhm.
I can we go over that
Okay.
part?
So part D, you'll notice that the answer for part D and part C is the same. And the reason why, let me clear this here. The reason why is because of this equation right here. Hold on. This equation, Ka is equal to the concentration of H+ times the concentration of A- divided by the concentration of HA, right? Now, at the transition point, I'm just using A instead of IND, right? Same thing, right? At the transition point, the concentration of A- is going to be equal to the concentration of HA, right? And if that's the case, then these two will cancel out. This will cancel out with this. So therefore, Ka will be equal to concentration of H plus. So what this means is that the pH is going to be equal to the pKa, which is equal to the pKa, I'm sorry, which is equal to 4.4. We got the 4.4 from the previous part, so which is equal to the pH, so therefore the pKa will be the same thing.
Okay.
All right?
Yes. Thank you.
Okay, so do we need to go through E?
Yes, please.
Okay, so basically in the case of E, the relationship between Ka and pKa is pKa is equal to minus log of Ka, right? So this is useful if you want to find a pKa and you're given the Ka value. However, the question is asking for the Ka value. Ka is equal to 10 to the minus pKa, right? So basically you use this if you want to find the Ka, if you already know what the pKa value is. And that's exactly what we use. We use that equation. All we have to do is put where we have the minus pKa, where the pKa is, we put the actual value of the pKa at this point, which is 4.4. So minus 4.4. And when you plug that into your calculator, you're going to get 4 times 10 to the minus 5. Please note that because you have one decimal place here, that means the answer here has to be expressed to 1 sig fig.
Okay.
So you may get some digits on your calculator display, but you have to round it off to 1 sig fig.
All right.
All right. Okay, do I need to go to do F?
Yes. Can we go through all of these, please?
Okay, good. All right. So again, let me clear this here. Okay, so the question says at pH 2.2, the indicator is blue, and you're asked to find out or tell if I'm sorry, the question didn't give you the blue color. I'm sorry. So the question just said black. It just gave a blank space there, right? And it also is asking for you to tell whether or not the concentration of the undissociated acid molecule is either greater than, less than, or equal to the concentration of the conjugate base. All right, so key thing you need to remember is this. What you're doing is comparing the pH to the pKa, right? So basically, I'm just doing this as a summary right here. If the pH is less than the pKa, what that means is that the concentration of the undissociated molecule, HA, is greater than the concentration of the conjugate base, right? And if the pH is greater than pKa, then the opposite is true. I'm sorry, this should be pKa. pKa, if pH is greater than pKa, that means that the concentration of the conjugate base is greater than the concentration of HA, the undissociated acid molecule, right? So this is basically what you're going to keep in mind. Now, there are within certain limits where, in fact, let me include a third line here. If the pH is, how should I put this again? Equal to pKa, if the pH is equal to pK, I'm sorry. Let me do this other way around. If the pKa I'm trying to think of how to word this correctly. All right, let me do this way. If the pH is equal to pKa plus or minus 1.
Oh, okay. You wrote that on the ones. Okay.
Oh, okay, right. Okay, good. So, right, if the pH is within that region, right, then what did I say? The color would be like if in the case of the indicator we're working with here,
You mix
it's
it.
blue, right? It would mix, right? So the color would be I'm just gonna write here color combined. All right. You know what I mean, right? The two colors would mix, right?
Yes.
Okay, all right.
Yes.
Now, so this is basically what we're using in order to answer which part? The F part, right? In fact, from F down to I, okay? So in the case of F, right, the pH is equal to 2.2 and the pKa is 4.4, right?
Right.
So because the pH is less than the pKa, that means that the concentration of the acid would be greater than that of the conjugate base.
So it would be blue.
And the color of the indicator of the acid, yes, you're right, blue. So therefore the color is going to be blue because
Oh, okay.
because HA is blue and A minus is yellow. You see what I'm saying?
Mm-hmm.
So that's
Okay.
F, right? Now in the case
Right.
of G, it's 7. pH is 7. But the pKa is still 4.4, right? So what do you think the answer is? Which one is
So
greater?
the IND is greater.
Right, or the conjugate base, right, exactly, would be greater than the concentration of HA, and that means the color is
Yellow.
yellow. Exactly.
Okay.
All right.
And the next one's the same thing.
Hold on, let me I'm sorry, hold on. Why is this thing not behaving? Okay. Let me just scroll down. Okay, for the next one, which is H. Yeah, same thing. Same thing as in the case of G. In fact, it's even more so true for H than G because the pH is even lower, right? So therefore, the pH is greater than the pKa, and therefore, the concentration of the acid will be greater than that of the conjugate base, which means it's yellow. Okay, good. I'm sorry, I misspoke. The conjugate base concentration is greater than that of the acid, so it's yellow. Okay, so in the case of H, hold on. Same as above. I'm just going to write same as above, or same as in G, right? Okay, now in the case of I, right, the pH is equal to what? 4.4, right? Which is the same as the pKa, right? So what does that mean? That means that the concentration of A minus is the same as the concentration of HA, right? Which means that the color is what?
Green.
Green, exactly. All right. And then in the case of J, 4.3. The pH is 4.3.
It would also
pKa
be
is it's going to be green because it's within that range that I mentioned, right? 4.4 is 0.1 above 4.3. So therefore, the concentrations would not be the same, but it would be slightly off, right? The concentration of the A minus would be slightly less. So that's why in the answer key, or in the answer that we discussed in class, I still said that the concentration of the acid, let me write that down, would be greater than the concentration of the conjugate base, right? But the color is going to be green because the difference is not that great, all right? Okay, so that's 4.3, that's I. Okay, let me erase up here. In fact, let me lasso all of this up here. Okay, so in the case of K, right? So now we're given a particular concentration of an acid, and it's nitric acid. Now the thing is, we all know, and I keep telling you guys, you need to remember the 6 strong acids, right? And nitric acid is one of them. So for 0.001 m nitric acid, if you were to find the pH of that acid, the pH would be equal to 3, right? Because the nitric acid is strong, which means that the concentration of H plus is going to be the same as the original concentration of the acid. And therefore, when you try to find the pH, that will be equal to minus log of 0.001. That is going to be equal to 3, right? So we're going to compare 3 to the pKa, which is, again, 4.4, right? And obviously, 3 is less than 4.4. So what does that mean?
That the color would be blue.
The color would be blue because the concentration of HA or HIND is greater than that of the concentration of A minus, right? So that's what happens in 0.001 m nitric acid. And then now in the case of L, let me get rid of this down here. Okay, so in the case of L, oops, let me carry that down here. They're giving you 0.001 m potassium hydroxide, which is a strong base, right? So in this case, the concentration of the OH minus would be the same, 0.001 m, which means that the pH would be equal to minus log of, POH. It would be equal to minus log of 0.001, which would be equal to 3. In fact, it should be 3.0 to be more accurate. This should be 3.0. Anyway, which means that the pH is equal to what? 14.00 minus 3.0 gives you what? 11.0, right? And 11.0 compared to 4.4, which is the pKa, tells you what?
That it's greater, so the concentration of A minus is greater than HA.
Exactly.
So the color is yellow.
Exactly. And that's how you do that.
Okay.
All right?
Yes. Thank you.
Is there any more after that? Let me see. Oh, that's the last one in that question. Okay. Okay, any other? Do we need to do number 9? I mean, not number 9, I'm sorry. The one after. Number 10.
Number 10 looks pretty. I don't know if I finished writing it down, but I think it looks a little simpler than 11. So is it okay if we go over 11?
Okay, so in the case of 11, they gave you the Ksp, they gave you the molar solubility. Oh, they're asking firstly for the molar solubility in water, and then it says it forms a complex, and the Kf is given for that complex. Calculate the molar solubility of silver bromide in 1.50 m ammonia. Okay, all right, tell you what, give me 5 minutes. I need to run to the restroom. And I'll be right back, all right? All right? Hello,
Okay.
can you hear me?
Yes.
Okay, all right. All right, later. Right back. Ah. Okay, I am back. All right. So let's start with the first part of the question, which says here to determine the molar solubility of silver bromide in water. So that is similar to a couple of the questions that we did before. I'm just going to go through it quickly as soon as I delete all this crap here. Okay, so first thing, of course, we will do is write down the dissociation of silver bromide, AgBr, solid, and that will dissociate to form Ag plus Br minus, right? So initially, you're going to have none of these. The change would be plus S, where S is a solubility. And at equilibrium, you're going to have S and S. So Ksp would be equal to S squared, which means that S would be equal to the square root of Ksp, which would be equal to the square root of, what's Ksp? 5.35 times 10 to the minus 13, right? So 5.35 times 10 to the minus 13, find the square root of that. And according to my calculation, I got round off to 3 sig figs, so I got 2.86 times 10 to the minus, oh, wait a minute, hold on. Let me do this again. This doesn't look right. Okay, I knew I did something wrong. So let me erase this here. I got the solubility to be equal to 7.31 times 10 to the minus 7, right? Okay.
That's what I got too.
Okay, good. So that's the first part, right? The second part says you're to calculate the molar solubility of silver bromide in 1.50 m ammonia. So the way I would set this up is I would recognize that the silver bromide is still undergoing the dissociation. In fact, let me erase. You know what, let me just continue down here. Right? So you're going to have still the silver bromide undergoing dissociation, right, to form silver ions and bromide ions, right? And the Ksp for this is, as we said before, equal to 5.35 times 10 to the minus 13, right? Now, there's going to be another reaction, and that other reaction is where the silver ions will react with ammonia to form the complex, and that is also an equilibrium reversible reaction. The complex is going to be AgNH3 2 plus. Now, because you have 2 ammonia here, that means you need to put a coefficient of 2 here, right? And they gave us the Kf value to be equal to 1.69 times 10 to the 7, right? So the formation constant, Kf, is equal to 1.69 times 10 to the 7, right? Now, so basically, you have to understand what's happening here. The first step is the dissociation, which basically produces the silver ion, which will react with ammonia in the second step to form the complex, right? And the thing is that because this complex is so stable, it basically will decrease the concentration of Ag plus, which means that the equilibrium will shift in this direction, which means that the solubility of the silver bromide will increase. So the resulting calculation should give a value which is less than this, right? This is the solubility in pure water. Whatever we calculate down here must be less than what we have here, right? So first thing we need to do after this, let me get rid of this here. Okay, so the first thing we need to do is add these 2 equations together. So when we add these 2 equations together, of course, as we always do when we're adding chemical equations together, is that we cancel out those items that are common to both sides. So the silver ions here and here will cancel out, right? So therefore, when you add everything together, you're going to end up with AgBr plus 2NH3, and then you're going to have AgNH3 2 plus Br minus. Whoops. Br minus, all right? Now, the question is, what would be the resulting K value for this? And you should remember from the third chapter that we discussed in this course that whenever you add two equations together, you multiply the equilibrium constants to get the equilibrium constant of the resulting equation, right?
Right.
So that means that K here will be equal to 5.35 times 10 to the minus 17 multiplied by 1.69 times 10 to the 7. And let's see what that gives.
It's
5.
the first one, 5.35 times 10 to the minus 13.
13. Oh, my bad. It's my poor handwriting that is, it's kind of hard to write with this particular type of tablet. Anyway, thank you. 10 to the minus 13 multiplied by 1.69 times 10 to the 7. And according to my calculation, this works out to be equal to 9.366. So 9.04 times 10 to the minus 6. All right? So that's the K for the result of adding those two equations together, right? So the next thing we need to do now is set up an ice table. Let's scroll down here a bit. So we need to set up an ice table based on this equation right here. So the initial concentrations in the second ice table is going to be, in the case of the ammonia, because that's what's given in the question. Well, firstly, we don't need to worry about the silver bromide because it's a solid, right? But in the case of ammonia, this is going to be 1.50, right? In the case of the complex here, it's going to be 0. And in the case of the bromide here, it's going to be 0 as well. The change that's going to take place, we don't know what that is, but I'm going to say that the change for the silver and the bromide ions will be plus S, right? And this here, because of the 2 here, and because it's reacting, this is going to be minus 2S, right? So at the end of this process, at equilibrium, you're going to have 1.50 minus 2S. Here you're going to have S, here you're going to have S, right? So therefore, we can write down that the K value would be equal to S times S, which is S squared, divided by 1.50 minus 2S, and all of that will be squared, all right? And we set that to be equal to 9.04 times 10 to the minus 6.
Okay.
All right? And then, basically, it's algebra from this point forward. Because you have two terms here and here squared, you just find the square root of both sides, right? And the left side would be S over 1.50 minus 2S, and that would be equal to the square root of 9.04 times 10 to the minus 6. Let me see what that gives. 9.04 times 10 to the minus 6. Find the square root of that. So according to my calculations, this works out to be equal to 3.01 times 10 to the minus 3. And then we do cross multiplication. We get S is equal to 3.01 times 10 to the minus 3. 3 multiplied by 1.50 minus 2S. And then we what do you call the term in math? I forgot what you call it. But anyway, you're going to multiply, distribute. You're going to distribute this within the parentheses here. So 3.01 times 10 to the minus 3. I'm going to multiply that by 1.50. And that part I got being equal to 4.52. All right. Times 10 to the minus 3. And then minus 2 times 3.01. Okay, so 2 times 3.01 times 10 to the minus 3. And I got 6.02. Why is this thing 6.02 times 10 to the minus 3 S, right? And then I bring like terms on both sides, which means that I would have to add plus 6.02 times 10 to the minus 3 S to both sides. And this would go with that. So I'm going to end up with S plus 6.02 times 10 to the minus 3 S equals to 4.52 times 10 to the minus 3, right? This part here, when you work it out, this is basically going to give you S equals to 4.52 times 10 to the minus 3. And the reason why that is so is because when you compare 6.07 times 10 to the minus 3 to 1, right? Basically, you're adding 6.02 times 10 to the minus 3 to 1. 6.02 times 10 to the minus 3 is a very small number. So that plus 1 is basically equal to 1, right? So therefore, the final answer is S is equal to 4.52 times 10 to the minus 3 M. And that's it.
Okay,
All right?
I have a question.
Yes, ma'am.
So you know how 4.52 times 10 to the minus 3 and 6.02 times 10 to the minus 3, they have they would go back the same number of decimal points. Does that make sense? Like,
Okay,
I'm trying to
depends
say,
on how we got. Okay.
is it 4.52 times 10 to the negative 3 smaller than 6.02 times 10 to the negative
Yes,
3?
but we're not adding 4.52 times 10 to the minus 3 to 1. We're adding 6.02 times 10 to the minus 3 to 1. So therefore, that's what we're looking at in terms of the size, the relative size or magnitude of 6.02 times 10 to the minus 3 to 1. 6.02 times 10 to the minus 3 is almost 0 compared to 1. So when you add it to 1, you're going to get 1. In this case, 1S. But you brought up something. You said something about sig figs, right? The 4.52 rounded off to 3 sig figs comes from the fact that we multiplied this number here by this number, right?
Okay.
So this is 3 sig figs here, and that's 3 sig figs here. You see what I'm saying? Yes, so that's how we end up with 3 sig figs for the 4.52 times 10 to the minus 3. All right? No, there's another part. Oh, I'm sorry. Go ahead.
No, it's okay. Also, so you know when we had S is equal to 4.52 times 10 to the minus 3 minus 6.02 times. So how did you know like to add 6.02? Like why not just subtract 4.5?
Oh no, you can't. Well, for one, you can't subtract. You know why?
Why?
And if I'm getting your question, you're asking why you can't simply subtract this from this, right?
Yeah.
Well, because this has an associated S term.
Oh, I didn't see that. Okay.
Okay,
Okay.
right.
Oh,
So
okay.
so in order, and we have an S term over here. So we're trying to get the S terms on the same side. And that's the reason why I added 6.02 times 10 to the minus 3S to minus 6.02 times 10 to the minus 3S on both sides, right? So
Okay, I'm sorry. That makes sense. I didn't even see that S. Okay.
Right, exactly. So that's the reason why.
Okay.
All right. No, I think there's one more part to this question that we need to answer. The C part, which says, what mass of silver bromide will dissolve in 175 mils of 1.5 M ammonia? So here we have the solubility. In fact, let me scroll down some more. Right, so we have the solubility. So to get the mass that would dissolve, in 175 mils of 1.5 M ammonia, this is what I'm going to do. I'm going to start off the 175 mils of ammonia. I'm going to convert that to liters. So you're going to have 1 liter over 1,000 mils. And then I'm going to multiply that by the molarity, which is the solubility, which is what we have right here. So this is going to be 4.52 times 10 to the minus 3 moles per liter, right? And then the last step, because the question is asking for the mass in grams, is the molar mass of the silver bromide, right? So we're going to have 1 mole of the silver bromide down here, and up here we need the molar mass. So let me go to my molar mass calculator. And I'm going to put in the formula for silver bromide, which is AgBr. Okay, so according to what I have here, the molar mass of silver bromide is 187.77 grams. And that's it. Whatever that gives, that will be the answer. So 175 divided by 1,000, whoops, times 4.5 times 10 to the minus 3 times 187.77. And according to my calculation, the answer is 0.148 grams of silver bromide. And that would be the answer for the C part.
Okay. Also, for part B, you know how we assumed that S was like less than, do we do the percent dissociation for that?
No, you don't know. When it comes to, and that's a good question, and I probably should have mentioned that in class. It slipped my my memory. It slipped my memory. You don't, when it comes to solubility product and these type of problems, there's no need for you to determine the percent dissociation, because pretty much in all cases, the percent dissociation is very, very small when it comes to solubility product and all that, right? You only use or do the percent dissociation when you're doing for weak acids and weak bases, right? That's the only time you do this percent dissociation. But for these kind of problems, yeah, these kind of problems, you don't need to do that.
Okay. And I think that's all my questions for this one.
Okay.
Yeah, I think I pretty much understand the other assignments, so I think that's all.
All right. Well,
Thank you. Thank you so much.
no problem. If you have any more questions, excuse me, I think I'll be here for a long time. So what you can do is call me at my extension 6202, and then I can create another link so that we can talk, just in case if you have any more questions for the rest of the day.
Okay, thank you.
All right, take care.
You too. Bye.
Bye.